chat real quick about it so you can see that there's application to this. So let's make it simple. Let's make it real simple. You know what? Before we even draw a scenario, if I'm in a train, all right, guys, focus. If I'm in a train and this train is going 50 miles an hour and it travels for 2 hours, how much does the train travel? Yeah. I'm in a train. It's going 50 miles an hour. And I'm on it for 2 hours. How much does the train travel? 100 miles. All right. So check it out. I have a situation. Let's draw that situation. Here it is in miles per hour. So I'm going to put MPH. And I'm going to put 50 here. And I'm going to put hours down here. And I'm going to say that's 2. So you guys just told me if I'm in a train and I'm going 50 miles an hour, you guys just told me that this train traveled how many miles? 100. Well, look at this. Does this area under this curve, will this area be 100? Yeah, not only that, it would actually also be 100 miles. Look, miles per hour, and I have this in hours. Miles per hour times hours is just miles, and you'll get 100 miles. Isn't that cool? All right, so what's the whole point? Okay, Chav, I can see how it's useful on this. All right, tell me. Assuming I have the same units, miles per hour here and hours here. But let's say this time that I have a variable speed, that this train goes at random speeds because of hills and turns and all that. Will area under this curve still give me distance traveled? Yes. So this is why calculus is so useful. And it's not just for this, it's for a lot of, you know what? I don't get into this until the very end, but I'm going to go ahead and tell you now. Look, if you go to the very last page, look at this. This is the medical purposes for you future medical doctors that are going. So check it out. I'm just going to read it out real quick. The number of liters of blood your heart pumps in a fixed time interval is called your cardiac output. For a person at rest, the rate might be 5 or 6 liters per minute. Hey, did you guys know that? 5 or 6 liters per minute. Wow. During a strenuous exercise, the rate might be as high as 30 liters per minute. Wow, that's a lot, guys. It might also be altered significantly by disease. How can a physician measure a patient's cardiac output without interrupting the flow of blood? One technique is to inject the dye into the main vein near the heart. The dye is drawn into the right side of the heart and pumped through the lungs and out the left side of the heart through the aorta, where its concentration can be measured every few seconds as the blood flows fast. The data in the table and plot shows the response of a healthy resting patient of injection of 5.6 milligrams of dye. All right, so what are they doing? In a nutshell, they're finding area under that curve. They're also doing dimensional analysis, but area under that curve to find how much blood is been pumped. Isn't that cool? So you can see how calculus is so useful, guys. Of course, are you going to be a medical professional calculating liters of blood at that moment? No, you're going to be tied to a machine, right? And the machine's going to do it. But you as a physician have to know like the math behind it. It found the area under that curve. See, so this is why, I just got the chills. This is why calculus is so practical, guys, because it can be used for many things. And this is just the tip of the iceberg. There's so much more. This is just barely the tip of the iceberg. And I'll stop saying that because I know if I say it over and over, it can get annoying. All right, we're going to go slow. We don't know how to integrate yet. We don't know how to find the perfect area under the curve. So we're going to find it the easy way with geometry. We're just going to break it up into pieces and add them up. That's it. That's all we're going to do. Does that make sense? So, Chop, I have no idea what you're talking about. You'll see. It's going to, there's some, okay, I guess we'll talk about it now. Example 1. A particle starts at x equals 5 and moves along the x-axis with velocity given t squared. Okay. For time t greater than 0. Using n equals 6, so this means 6 rectangles. What are you talking about, rectangles? We're going to cut everything up. Bless you. We're going to cut everything up into a rectangle, guys, because it's easy to calculate the area of a rectangle. Of equal width, approximate the total distance traveled from t equals 0 to t equals 3 using LRAM, MRAM, RRAM. Once you find the total distance traveled, where is the particle at t equals 3? It's asking for a lot. Let's just find the distance traveled right now. So what does LRAM stand for? It stands for left rectangular approximation method. What do you think RRAM stands for? Yep, right. It's exactly that. Right rectangular approximation method. What do you think MRAM stands for? Mid. Not like, oh, it's mid, like middle, right? It's like mid. Mid rectangular approximation method. Okay, before you guys start Googling, if you Google and you don't see any of these, like Chop, that's not what Google says. Some textbooks, instead of saying rectangular, will call it Riemann. I can never pronounce it right. Raymond. I think if you go to dictionary.com and put that in there, it says it Raymond. Left rectangular approximation method and left Riemann approximation method are the same. So relax. Cool or not cool? All right. All right, let's go ahead and start. I guess if you go to the next page, it's blank on purpose. Oh, why is it blank? Okay. Title it NRAM in the top left-hand corner. And if you have colored pencils, this is a good place for colored pencils. I'm going to exaggerate quadrant 1. They told me my velocity equation was t squared. So I'm going to exaggerate a parabola, and then from what time to what time? 0 to 3. So I'm going to do this, guys. Here's my parabola, 0 to 3. I exaggerated it. I'm going to say that's 3. I'm going to say this is 1. I'm going to say this is 2. 1, 2, 3. They want me to use how many rectangles? 6. I'm going to write n equals 6. And I'm going to start by using black. So that means, bless you, bless you. If I'm using 6 rectangles, that means my change in x, the width of each rectangle, let's see, 3 divided by 6 equals 1/2. The delta x in each rectangle is a half. And I guess I should put the 3 came from 3 minus 0, and the 6 came from n equals 6. Rightmost minus the leftmost divided by how many rectangles I want. So I'm gonna choose blue. No, I'll stay with black. Bam, bam, bam. Okay. I'm gonna go slow, guys. The keyword is leftmost. So I'm gonna go to the curve, and that's gonna dictate my height. My first rectangle has an area of 0 because I'm right on the x-axis. Chav, I don't understand. I went to the leftmost point. I put a point on the curve, and then I just went. You'll see it. You'll see it right now better. My second rectangle, I go to the curve. The t squared, the red. Put a point, go straight down, and then go horizontal. And then there's my second rectangle. Slope of 0 at the top. They're just rectangles, guys. My third rectangle, go to the curve, put a point, and look, notice that it's starting at the leftmost corner. My next rectangle, point, I'm at 1.5. My next rectangle, and I'll slow down. It doesn't have to be perfect, guys. My final rectangle. And there it is. Let's find the area of those rectangles. That's n equals 1 right here. N equals 2. N equals 3. You don't need to know that, but I just want to make sure that you have good notes. I find area of a rectangle just doing length times width. Length times width. So the width of each one is 0.5. And yes, you can factor out the 0.5. The height of the first one is 0. or I guess let's be technical, 0 squared, plus width, 0.5. The height of my second rectangle is whatever 0.5 squared is. Is anyone confused how I got the 0.5 squared, guys? The equation of that model of that curve is t squared. So if I want the height, I put the x value in there and I square it. My third rectangle, the width, all the width for all of them are 0.5. What's the height? 1 squared. Width for this one is 0.5 again. And 1.5 squared. 0.5 again. 2 squared. 1, 2, 3, 4, 5. Okay, one more. And my last rectangle, and is dictated by the x value of 2.5, and I square it. All I did was width times height, guys, for all of them. Cool or not cool? All right, guys. 0 plus, yeah. You know what? Just tell me what the whole sum is. You can factor out, I guess. You're going to need a calculator, guys. You need a calculator. This is calculator heavy. I think it's it. Oh, it did. It just got to restart the cycle. Turn it off and turn it back on.
Oh yeah, you're right. I got scared, sir. That was horrible. My heart died.
All right, guys, tell me what that number is. If, hopefully, you'll match whatever number I get here. Make it an attempt, guys. Okay. I got 6.875. Is that what you got? Okay. Yes. It doesn't matter. You can just go like this, just verbatim. This is just a hack. I typed into my y1 x squared. See? And then I just went, I factored out the y, the 0.5, and then just, you know. If you have physics, maybe you could have, if you have, where do you do this? In physics and statistics, maybe you could have done a sum using the sum feature. Oops, I messed up. What is this doing? 0.5 times 0.1, 0.2, 0.3. Okay. There's something wrong there. All right. All right, guys. Focus, focus, focus. So we've only done LRAM. Is this an under approximation or over approximation? Under, because look at all the area that is uncounted for. Does that make sense? All right, now let's do an RRAM. So I'm going to change colors. Well, my rectangles are going to change colors. I'm going to do this. I'm going to go RRAM. And, oh, man, do I have enough space for two more? Okay, I'm going to use this half of the page, and then I'll do the other half for MRAM. All right, here we go. You guys ready? For RRAM, use the rightmost point for your first rectangle. So in the first delta x, so between 0 and 0.5, you go to the rightmost point, bam, go straight down, and then go to the left, go back to that point on that curve, and then there's your first rectangle right there. See how we did it? Second one, go to the rightmost point. So this is why it's called RRAM. And continue the pattern. You should have 6 rectangles. Not perfect. My rectangles kind of suck, but that's okay. And I'm doing the same thing, guys. So let's see. I'm going to add them up. 0.5. Since all of them have a 0.5, because that's my delta x. And then eventually we're going to put that at the very end there. But for now, we're rookies, so that's fine. Open parenthesis, and I'm factoring it all out. So I'm just going to type in 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared plus 3 squared. There should be 6 terms for 6 rectangles. And all I did was factor out the 0.5, guys. Oh. Can someone do this and type it in the calculator? It should be a number bigger than, definitely bigger than 6.875. What'd you guys get? 11.375? Yeah, that's what I got. All right, guys, focus. All right, now I'm going to try MRAM. So let me see if I can draw it. Let me put a cut right here first. Oh, what? Yeah. All right, guys. Okay. So how does MRAM look? All right, guys, focus. You're going to start between 0 and 0.5. So between 0 and 0.5 is at 0.25. You're going to have a little bit above the curve and a little bit below the curve. See? Then you're going to go between 0.5 and 1, so 1.25. You're going to put a point on that curve. And you go to the left and then down and then to the right and then down. A little bit above and a little bit below the curve. Don't worry, I'm going to do it again. All of them are still delta x of 0.5, guys. So between x is 1 and 1.5, I go to 1.25 on the curve. I put a point at x equals 1.25, whatever that y value is. And I go to the left, down, and then right, down. And a little bit above the curve, a little bit below the curve. All right. There it is, guys. Someone go ahead and do this math here. I'm going to factor out the 0.5, 0.5, and then you're going to go 0.25 squared plus, and just keep adding 0.5 to that, right? 0.75 squared plus 1.25 squared plus 1.75 squared plus 2.25 squared plus 2.75 squared. That should be 6 terms. 1, 2, 3, 4, 5, 6. Yep. 6 terms for 6 rectangles. I factored out the 0.5 with height, with times height, with times height. Can someone do that and tell me what answer you get? And I'll do it here as well, but I'll factor out the 0.5 and then. All right, guys, practice. Dang it.
Triangles? It's actually really good. I got it. This is cool. No. Connection.
All right, guys, try. What'd you guys get?
Yeah.
Okay, before I push enter, what'd you guys get? Good job. 8.9375. Okay. All right, guys. These are all approximations. Good. Hopefully it's intuitive, I hope, that you can tell that the rightmost, in this case, notice every rectangle is above the curve. Later on, we'll start talking about over and under, but I hope that intuitively you can tell that the RRAM is an over approximation, the LRAM is an under approximation, and the one that best approximates this curve is probably, in this case, the MRAM. Do you guys see that? Okay. We haven't answered the question yet. All right, guys, I need you guys to focus because this is a big deal of what we're about to do. What's up?
So the RRAM is like the rectangles to the right of the.
You reference your delta x and you start at the rightmost.
Oh.
See, each rectangle has a delta x of 0.5, and you start at the rightmost and then 0.5. Go to the curve. Boom. This delta x, this delta x, this delta x.
Oh, that's what the
That's why the left starts at the left, the right starts at the right. All right, guys, focus. All right, turn to the next page. We're still in example 1, and we're going to answer it at the top margin. I don't know. I haven't decided yet if I want to give you that program or not. Maybe I will in your calculator. So check it out, guys. At the university, they use something called, well, it depends what university you go to, but the popular one, UT and A&M use something called MATLAB. Sometimes they call it, well, it's a different one, but they're all the same, more like Maple, and there's Mathematica. They're all programming languages, CASs. Wolfram Alpha is a product of Mathematica. And your professor, so at A&M, if you go to A&M College Station, they're going to tell you that they want you to take Cal 1 again because they do MATLAB in their Cal 1 courses, and they're going to make you do like this, where you're going to create a program where you're adding up infinite amount of rectangles, and they want to see it, right? They want to see you programming it. Relax. You can just program it on the side. Practice MATLAB. It's not that tough. You can learn it on your own, or swing by. And I think for students it's free. You can download MATLAB for free for students. For educators, I think you got to pay like $500 or something like that. All right. So here it is, guys. Look, for 6 rectangles using LRAM, they got 6.875. For MRAM, they got 8.9375. For RRAM, they got 11.375. Those are the same numbers we got. And then look, 12, 24, 48, that's just how many rectangles they use. Look at all the way at 1,000. LRAM, MRAM, RRAM. Now, here's the question for you. So this is why limits are important. If n approaches infinity, if I use an infinite number of rectangles, would all three of these converge at the same number? Yes. What number is it converging to?
Oh, wait.
Yeah, one number. It's converging to 9. See, so this is why computer software is so important, guys. No, you're good. So here it is. Distance traveled. So here it is. Here's my answer. Distance traveled by particle is 9 units. All right, that's part 1. And then what else did they want? They wanted, I think, the position, right? Yeah. Okay, my position initially was 5. Okay, here's how you say your initial position. It's motion in the x-axis. So I'm going to say this. My initial position is 5. Where is your position at 3 seconds? I moved 9 units. What is it? Not 45. No, it's a safe space. You're good. Okay.
5 plus 9, is that what I have to do?
Yes, that's it. Guys. No, you're good. Guys, your initial position was 5. You moved 9 units to the right. 5 plus 9. Okay. You know what? This is important because this is real life. So I'm going to talk to you guys real quick. If you're, hopefully you have a tow. Okay. If you're ever stranded on the highway, do you ever see some markers on the highway? Like when you're driving on I-10, do you see like a marker sticking out with a number on it? Those are called mile markers. They're used for when, it says mile marker 23, then mile marker 24, then mile marker 25. So when you pull over on the highway, guys, and you need a tow truck, here's what you say. You call your tow service and you go, I'm on I-10 West. I'm between mile markers 23 and 24. And that way the tow truck driver doesn't like he just goes real quick. If you just tell him, I don't know, I'm on I-10, I went blah, 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 of course it's going to take forever. So now you know. So next time you're driving on the highway, guys, all right, guys, focus. Next time you drive on the highway, look to your right for a mile marker and notice some numbers. So if you ever get stranded, you can be on a mile marker 23 on Highway I-10 West. And then they'll find you real quick. So hopefully now you know. That's something important. Okay. Now we at least learned something there. All right, guys. Here we go. Let's start. Let's continue. So it says example 2, true or false. It says if f is a positive continuous increasing function on a to b. So let's see, positive continuous increasing. So I'm either going to be like this or like this. Positive continuous increasing. Then LRAM gives an area estimate that is less than the true area under the curve. Justify your answer. Well, I don't know. Let's find out. Let's do 2 rectangles. If I do 2 rectangles, boom and boom. That's for that. And let's say if I'm continuous like this, boom and boom. Yep. Does that look like it's going to be underestimate?
Yes.
True. As long as you're continuous, positive, and increasing, regardless of concavity, it's going to be an underestimate. All right. Example 3. If an MRAM sum with n equals 4 rectangles of equal width is used to approximate the area enclosed between the x-axis and the graph of y equals 4x minus x squared, the approximation is? Okay, let's see. Ready, guys? I'm going to go ahead and factor out an x so I can see the symmetry here. 4 minus x. Okay, so it's 0 at 0 and 0 at 4. So that means I have a vertex at 2. So it probably looks something like this. Are we still okay? All right, here we go. I'm going to draw my rectangles. What did they want me to use? MRAM. So how do I figure out my delta x? I go 4 minus 0 divided by 4. So my delta x is just 1. So let's see. Boop, boop. 1, 2, 3, 4. Perfect. And I'm using middle. Let's see. So hopefully it's symmetric and it's perfect. Oh, man. There we go. 1, 2, 3, 4. It looks like it's not, but it's not perfect, so that's fine. There it is. I'm going to find that. Chop, how do you find that? All I'm doing is width times height. 1 times what's my height? My height is dictated by this curve. So plug in this value here is 0.25. Nope, that value there is 0.5. Dummy. The delta x is 1, guys. So I'm putting in a 0.5 in here. So you know what? Let's just use our calculator. y1.5. We'll help you right now, right? In a little bit. Plus y1 1.5 plus y1 2.5. These should be the same. Plus y1 3.5. All right. And all right. Do you guys know what I'm doing? No? Okay. I'm just doing width times height. The height is dictated by the curve, the y curve. So how do I figure out the height? I just plug in my x value. I'm at 0.5, so I plug in a 0.5 into this. Because I'm using MRAM. The delta x is 1. So this delta x is 1. So I'm using the 0.5 to figure out the height of that rectangle. Same thing for this one. I'm not using 1 or 2. I'm using right at smack in the middle, the 1.5. My drawing just sucks. Same thing for this one. It's symmetric on y equals 2. So this should have the same value as this. I'm using 3.5 to figure out the height of that. I'm plugging in 3.5 into the equation to figure out the height, to figure out the y value. Ask me, guys. I decided to use technology because 4x, I didn't want to multiply by a decimal and then square a decimal. So look, all I'm doing is I'm typing into here. I'm just going to type in, what am I going to type in? 4x minus x squared. So practice, guys, because you're gonna have an exam. 4x minus x squared. Type that into y1. And because it's 1 times everything, 1 times height, base times height, base times height, they're all 1. So do I got to put 1? So I can just go alpha trace y1, and I plug in 0.5. That's a height at 0.5, the output of that. Plus alpha trace y1, 1.5. Plus alpha trace y1, 2.5. And then the last one, plus alpha trace y1, 3.5. And I push enter, and there it is. That is the area. Because remember, this y1 0.5 just gives you the y value, right? It just tells you how high it is. Does that make sense, guys? Bless you. Bless you. Look, it'll make sense with this one because this one's a visual one for you guys. All right, I'm going to go slow. An LRAM sum with 4 equal subdivisions is used to approximate area under the sine curve from 0 to pi. All right, a little bit of pre-calc. It's baby. What is sine of 0? 0. What is sine of pi? 0. So it looks like this. We're right smack in the middle. It's pi over 2. Well, it's not perfect, but that's fine. How many equal subdivisions do I have? 4. So your delta x of each rectangle, guys, delta x just means the change in x, right? The thickness of your rectangle. Your rightmost point minus your leftmost divided by 4. I usually don't show the 0, guys, but I'm showing it now just to. So every rectangle has the delta x of pi over 4. Yay or nay? All right, let me see if I can draw it. Boop, boop. Okay. Which one am I using? Leftmost, rightmost, or mid? Leftmost. So look, here's my first rectangle. From here to here. Do I have a rectangle? No, it's the 0. That has the area of 0. Here's your second rectangle. I'm using the leftmost, guys. The leftmost. Here's your third rectangle. Here's your fourth rectangle. Ask me, Kunduru. Dime. How does Fonzie say? Dime la 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 la. No? Okay. You know what I'm talking about. It's with Demi Lovato, I think. It's a song. I'm thinking, okay. Yeah, Fonzie and Demi Lovato. You never heard of it? I heard it at graduation in 2023. Okay. Sorry, guys. Sorry. All right. That's it, guys. We're done. Baby pre-cal. Let's see. Check it out. Guys, focus. I'm going to factor out a power 4 for all of them. Power 4. Parenthesis. What sign of 0? 0. Plus, here's my second rectangle. Here's n equals 2, n equals 3, n equals 4. What is sine? This is power 4 right here, guys. And this is 3 power 4 right here. And that's pi right there. What is sine of power 4? Square root of 2 over 2. Plus, what is sine of power 2? Not 0. 1. What is sine of 3 power 4? Square root of 2 over 2. Good job. All right, let's look for that answer. Is it in there? There it is. And then finally, we already talked about this. I was so excited. Look at the little dimensional analysis that they're doing. So this is all you're going to be practicing, guys. You're just going to be practicing finding area into the curves with rectangles. And that's all we're going to do for now. When we come back, make sure that you bring your A game for Monday because we're going to need it. Especially if you do not know how to use the summation. But don't worry, we'll practice.